Hello, everyone. Welcome to our talk on public and bias-resistant randomness. This is a joint work with a team from Trinity College, EPFL, University of Bonn, and Yale University. Our talk will consist of 4 main parts. First, we'll motivate our project. Then we'll present 2 protocols for randomness generations we proposed. Then we'll continue with implementation, some experiments. We'll conclude with a few remarks and a quick demo. First, let me motivate the need for public randomness and explain why generating it is actually very hard. Public randomness, unlike secret randomness we're used to, that we often use for secret key generation, is collectively used. It has to be unpredictable ahead of time. However, past a certain point in time, when we're ready to use it, it doesn't have to remain secret. There are many applications of public randomness. They include random selection, lotteries, election audit, games for team assignments, protocols for parameters and scalability, and crypto for, let's say, challenges in zero-knowledge proofs, to name just a few. Unfortunately, there are a lot of real-world examples of rigged or failed randomness, and consequently, rigged or failed public random choices. In the Vietnam War draft lottery, the dates representing birthdays were not sufficiently mixed before drawing the order to appear for induction. Hot and cold balls were used to rig European soccer competitions. And finally, an insider had a pseudo-random number generator that was used to choose winning numbers for the Megabucks lottery. And it turns out that public randomness is not a new concept. There has always been a need for that. And perhaps in the past, a large book of random numbers published by a trusted source was sufficient. Today, it's not. Today, generating those numbers is hard simply because we face big issues of trust and scale. And these 2 issues are what we address in our work. So we set out to achieve a decentralized public randomness protocol in very well understood and commonly used T out of N threshold security model. We had 5 specific goals in mind. First, availability. We wanted to ensure a successful protocol completion even in the presence of dishonest parties. Unpredictability. We wanted to make sure that randomness is not revealed until a very well-defined point in the protocol. Unbiasability, such that the output is distributed uniformly at random, even in the presence of an active adversary. Verifiability by third parties, something that is very essential to public randomness. And finally, scalability, so we can run our protocol with potentially hundreds of participants. There are 2 main approaches to public randomness that require trusted third party, such as the NIST randomness beacon, and the ones without. Approaches without TTP include Bitcoin, slow cryptographic hash functions, lotteries, financial data. However, those require unusual trust and hardness assumptions. Examples of approaches that share our security model include coin flipping and distributed key generation. Unfortunately, those don't scale past tens of participants. So at first, it seems that choosing public random numbers is simple. The most common approach is to combine random inputs from all participants under the false assumption that if we have one honest party that contributes proper randomness, then the output will be sufficiently random. This approach provides no security because the last node has complete control over the output because they can choose their input after seeing everyone else's input. We can address that issue by using commit and reveal approach to force all the parties to decide on their inputs up front. However, we only get unpredictability out of this approach because the last node can still, the dishonest node can choose not to reveal and force a protocol rerun. Lastly, we can fix this availability issue with secret sharing. This works, however, it fails to provide full bias resistance because dishonest parties can distribute bad shares, forcing honest parties to recover inconsistent randomness. And this brings us to ranked share, a protocol that applies verifiable secret sharing and a point of no return strategy, something that is not new and has been used in the past. This approach achieves the 3 main properties we wanted to achieve. However, it's only verifiable by the participants, not third parties, and again, doesn't scale well.
Look at our 2 randomness protocols, RandHound and RandHerd, which target different deployment scenarios. For RandHound, we particularly want to achieve or improve on top of the properties that RandHerd provides. Namely, we want to achieve verifiability by third parties, and we also want to improve on the scalability of RandHerd, which is quick. So for that, RandHound is a client and server randomness scavenging protocol where an untrusted client, here depicted in yellow, uses a large set of nearly stateless and independent servers, depicted in gray, to generate this collective randomness. And what the client does is he's generating a configuration file that contains like the list of participants, a timestamp when the protocol run is scheduled, and the purpose of the output random. And then he's sending this configuration file to the service, initiating the protocol run. RandHound is a one-shot approach. This means that if the protocol run fails, the client would need to regenerate the configuration file and start from scratch new. As an example, you can take a lottery authority which wants to generate the winning numbers by choosing such a collective randomness. And the lottery would commit to the lottery parameters such as time, purpose, and participants, and then execute the protocol and works together with these reputable independent parties, which are the servers, to generate the collective randomness. So there are these two main properties that we want to achieve with RandHound. Namely, the first is public verifiability, and how we do that is the first building block that we use is a scheme called public verifiable secret sharing, which generates shares that are encrypted but can be publicly verified by third parties thanks to zero-knowledge proofs. And in particular, this allows us to implement a communication pattern where only the client, all the communication only happens exclusively between the server and the client, and there is no server-to-server communication. Another building block that we are using is collective signing, which allows us that the client publicly commits to their choices, which are double-checked by all the servers. And then the client, since he's like the center of this protocol, he's collecting all the messages during one protocol run, and from that, he's creating a protocol transcript, which allows afterwards to replay the protocol and thereby verify the collective randomness. The next property that we want to achieve is scalability. When we are using this secret sharing scheme, we have now the problem that when the number of servers is too big, then the secret sharing becomes very expensive. So what we are proposing is we shard the participants into constant size groups and then only run the secret sharing within those groups. And the collective randomness is then that every group generates an output, and we combine all the outputs of the groups to finally get our collective random value. The problem that we are facing here, however, is that how should we assign the participants to the individual groups? Ideally, we want to do so randomly because we have to assume that some of the servers are malicious. But for that, we would need unbiasable randomness, which we don't have yet. So the approach that we are proposing here is that the client actually selects the server grouping, and we designed RandHound in such a way that all the client can do is affect its own availability, which means that the most thing that he can do is run a self-DOS attack. And the security, we guarantee the security of the protocol such that the client cannot bias, for example, the output by using the pigeonhole principle, which allows us to say that at least one group is not controlled by the adversary with very low probability, and that we are using collective signing, which prevents the client from equivocating on the output by letting the service double check on the commitments of the client. As a summary, RandHound achieves all properties that we set out to, and it has a linear runtime complexity, assuming that the size of the groups is constant. And in the next part, we'll see how to further improve on the scalability of the RandHound protocol.
So in the previous protocol, we had randomness generated on demand by a client who is fully in charge and fully responsible for a protocol run. Now, in our second protocol, RandHerd, we would like a continuous stream of randomness in a way that doesn't require any of the nodes to be fully responsible for the process. RandHerd relies on a leader that is only trusted with availability, which means that the leader simply coordinates the process among all of the nodes. We also want to improve on the verification. We want the verification to be efficient, both in terms of the size of the proof and the time it takes to do so. We want it to be a single Schnorr signature. Finally, we want to improve on the linear performance on Rand-Hound. We do so by designing RandHerd to be a decentralized randomness beacon built as a collective authority, which is a potentially large set of servers that cooperate together in an efficient and publicly verifiable manner. The main idea behind RandHerd is to create our collective randomness as a series of collective Schnorr signatures on a series of timestamps. This gives us a small proof size and good logarithmic complexity. Unfortunately, we have to address the availability problem. Some nodes might fail, intentionally or otherwise, and once they do, the signature will not be a function of everyone's input, and that would allow the adversary to affect the output. The output would not be bias resistant. We address this problem by applying threshold Schnorr signing, which means that we can create a signature in the presence of T out of N signers, which will allow us to tolerate failures. Collective randomness, in this case, will be an aggregate of all of those collective signatures generated by the respective groups. RandHerd has two main parts, setup and a run function. The goal of the setup is to set up the stage for this continuous randomness generation. In the setup, we first elect a temporary leader, for example, by choosing a node with the lowest ticket generated using verifiable random function. Once that happens, we'll use that temporary leader to run Rand-Hound, our other protocol, to get good randomness. Then that good randomness will be used to divide servers into secure groups, and those groups will run TSS. Each group will further create its own public collective key. And lastly, those group collective keys will be combined together to create the overall public key for the entire RandHerd. And that key will be endorsed by all the participants in a run of cozy collective signing. And this brings us to the main part of RandHerd, where the continuous randomness generation happens. We do so by having the authority leader elected using our good randomness from Rand-Hound broadcast a series of timestamps. Those timestamps are collectively signed, first by producing group Schnorr signatures within those groups that we securely set up previously. Then those partial signatures get combined, and the overall collective signature of the entire RandHerd is output as the randomness. Verification is nice and simple. Our random output is CR, the collective Schnorr signature on a timestamp, can be checked as a single Schnorr signature under the collective key of RandHerd. This approach allows us to achieve all the properties we set out to achieve. And specifically, it allows us to get much better scalability simply because we achieved logarithmic performance given a constant group size C.
Okay, so in the next main part of our talk, we will look at the implementation and experimental results. We implemented all the presented protocols and the underlying building blocks in Go. And for that, we also used the available DDIS libraries, which you can check out on GitHub under the depicted link. And for the experiments, we had a detail lab setup of 32 physical machines. And to simulate more real-world network conditions, we restricted the network bandwidth and the round-trip latency. For RandHound, we measured the time it takes to generate and verify randomness for up to 1,024 nodes of varying group sizes. As a takeaway, it takes 290 seconds to generate and 160 seconds to verify randomness in a setup of 1,024 nodes and a group size of 32. In the same scenario, we also measured the total CPU cost of the client and all servers. And as a takeaway, again with 1,024 servers and a group size of 32, it takes roughly 10 CPU minutes to do one RandHound run, which corresponds to less than 2 cents on Amazon EC2. For RandHerd, we also measured the total randomness generation time for up to 1024 nodes with groups of varying sizes. And again, as a takeaway, it roughly takes 6 seconds after a single 10-minute setup in a setting with 1024 nodes and a group size of 32. This last graph shows that RandHerd indeed achieves this logarithmic complexity given a constant group size. Finally, to conclude our talk, we showed you that the generation of public randomness faces two main issues, namely trust and scale. And we proposed two protocols in the T of N threshold security model, which achieve all the 5 properties that are depicted here. Specifically, RandHound has a linear complexity, assuming constant group size, and RandHerd has a logarithmic complexity. For more information on the code, you can also check out our GitHub project. So now, in the final moments of the talk, I want to show you a small demo. So can we please go to the website? Thank you. So here you see a randomness beacon that we set up under the link pulsar.ddis.ch, which uses the RandHound protocol and a 64-node setup. And as you can see, there is a bar going from left to right, and every 30 seconds, the JavaScript grabs the generated randomness from the service that is running in the background. And now can we please scroll down a bit? Thanks. To retrieve and verify the randomness, you have to install Golang and then execute a few commands, and then you can locally on your computer request randomness and verify it locally. Okay, thanks. Please back to the slides. Okay, that's it from my side. Thank you.
Hi, Aline Tomescu, MIT. Thanks for your talk. I think it's a really great project. Could you go back to the RandHound slide where you overview your system?
Okay.
I have a particular question about that. Yeah, so you said here that, so the client is someone like a lottery, right? Like a lottery manager. So suppose we have this black box and we can generate randomness, which is a really cool primitive, and now I'm a lottery, and I want to use this black box and prove to you that I did it verifiably, publicly. But it seems that I can still do this n times until the result, I'm pleased with it and I can give the lottery winnings to my friend, right? So it seems that, I'm just saying maybe as future work, is this a direction that you guys have considered? How do you prove also that you only engaged in this protocol a limited amount of times or something like that?
So with RandHound, that's indeed right. So the client could abort the protocol, but that's also why we said this is like a one-shot approach. And in the case of a lottery, if the lottery really fails to finish the protocol and output the randomness it committed to, then all kinds of alarm bells, of course, should go off.
So I'm not saying abort. I'm saying just finish and then run again. And then finish, and then run again.
Which is basically the same thing, right? So the client can just decide to abort and then run it again. But at that point, if the client to the committed time is not delivering the randomness, then all kinds of alarm clocks should go off. And there are indeed also approaches that we are considering where in the end all the participants end up with the same random string. But this, of course, has a much higher computational complexity than RandHound.
Thank you.
Hi, Aniket Kate, Purdue University. So my question is again regarding RandHound, kind of similar, but if the client is the one who is going to choose the group, can he make sure that, can there be a situation where he wants to make sure that he can trick, so by making the groups such that all of them gives the randomness as he wants? Because the assumption is you want one group to be honest. But is it possible that if it is up to him, he'll pick the group so that no group is honest and then he can play or something?
So no, thanks to the pigeonhole principle, you cannot do so, right? If you have H nodes and you have to arrange them into groups, right, at least one group will have higher than average number of honest nodes. And we set up the threshold recovery to be such that they need that extra honest node, so it will not be possible. And for us, it's enough that this happens for at least one group. With high probability, it will happen for more groups. But just because we have this guarantee of a single uncompromised group, this will not happen.
Okay, so you're assuming overall you still have honest majority, and that's the reason pigeonhole. Okay.
Correct.
Hello, Mahdi Zamani from Visa Research. Very nice work. So I have a question. So you mentioned that the failure probability is constant. So it was like something like 8%. I mean, less than 1% failure probability. So it seems that every multiple rounds of running the generating randomness, the algorithm fails. I mean, with probability 1 after that number of rounds. So I want to know how. So probably you need to run the setup again from scratch. Everything is from scratch. What percentage of the costs that RandHound and RandHerd have? I mean, over say 2 hours of running over this setup, running the setup again. What percentage of the time and expenses will be wasted for running the setup again and again?
So for RandHound, this is like really just an on-demand approach, right? Because you just have these servers out there which do not know of each other, and the client just comes and grabs the randomness. For RandHerd, you indeed need to rerun the setup, and this is like, as we've showed before, for 1,000 servers, it's roughly 10 minutes to reset up the whole process. But then we assume, since we then have these groups assembled, and since they are using threshold crypto, we allow actually that some of these servers in the groups fail.
And how long can I run the? You said that's every 6 minutes I can generate 1.
6 seconds.
6 seconds, sorry.
6 seconds.
And how,
well,
probably around 2 hours.
You can, I mean, this is also under the assumption that we are facing an active adversary. So if the system, of course, is not under attack, then you can just go and run it all the time. And then maybe, let's say, you can do a reset up every week or so to reshuffle the groups, or if some servers fail and are unresponsive, then in a new setup you don't want to have them, of course, or the new servers appeared and you want to include them in the next setup phase.
Thank you.
All right, let's all thank Eva and Philipp and all the other speakers in the session.